Aloha, my name is Jerry Adams. I'm a rising senior at Chaminade University of Honolulu, and my project is the analysis of computer network intrusion through malware detection using statistical models. Introduction. Computer network intrusions or unauthorized access to a computer system is usually mitigated through the use of intrusion detection system, IDS, also known as a firewall, which is a network device that monitors and controls incoming and outgoing network traffic. One of the main features of a firewall is to block malware, which is software that is intentionally designed to cause damage to a computer system. However, traditional firewalls rely on known malware, therefore limiting their detection of new or unknown malware. An emerging method of improving a firewall is the use of malware detection to identify anomalous or malicious network traffic. This project utilizes statistical models for identifying anomalous network traffic and detecting malware among the normal network traffic. Problem statement. The problem is to differentiate or detect malicious or anomalous network traffic from normal, non-anomalous network traffic using statistical models and machine learning algorithms. Dataset. The dataset I utilized is UNSW-NB15, a public dataset that is well known within cybersecurity circles. It was created by the Institute for Cybersecurity at the University of New South Wales, Australia. The dataset is a packet capture of the network traffic that was generated using simulation software to simulate computer network attacks on a computer network, purposely sending malware such as viruses, worms, and ransomware through the network. The packet capture consists of raw network data such as IP addresses, network protocols, file byte sizes, date, time, and duration of the connections. The data set is quite large, consisting of 257,673 records with 45 variables. 41 are numerical, 2 categorical, and 1 discrete. The discrete variable is the label that will be used to help train the machine learning algorithm. The labels were 0 to denote normal traffic and 1 to denote malicious traffic. Methods. The methods used were the programming language Python and Jupyter Notebook with Pandas, NumPy, Matplotlib, Seaborn, and sklearn libraries. The first data wrangling method I performed was splitting the data set into test and train subsets. This was done in order to test and train the statistical models. The test set was 32% of the total, or about 82,000 records. The training set was 68% of the total, or about 175,000 records. The statistical models I chose to use to try and predict the malware were random forest, decision tree, and naive Bayes. I chose these models because they were the most accessible from the libraries that I had in Python. Moving on to visualizations. For visualizations, figure 1 is a simple computer network topology in order to give context and visualization of a network intrusion. From the left side of the diagram, an attacker sends malware from his computer over the internet and onto a end user pictured at the right side. Note that the intrusion detection system firewall sits in between the internet and the end user's network. This is where the firewall protects the end user's network and computer, filtering and controlling all traffic that flows through, hopefully stopping any malicious traffic from going through. Figure 2 is a breakdown of the labeled data, normal versus malicious network traffic. The y-axis are the number of connection instances going across the network. So as you can see, roughly half of the connections are deemed malicious, which usually isn't something you want to see on the actual real production network. But for my purposes, this is good because I want to train the model to detect the malicious traffic. Figure 3 bar graph depicts the breakdown of the malware by classes or types. There are 8 different malware classes. The top 3 most prevalent malware classes in this dataset are recon at 32%, backdoor malware at 20%, and DOS denial service malware at 19%. Moving down to figures 4, 5, and 6 are the confusion matrices of the 3 statistical models or classifiers used on the test set. The best performing classifier was decision tree. Its true positive was 58%. In other words, a classifier that predicted the malicious traffic as being actually malicious at a rate of 50%. The next best performing classifier was random forest at 53%, and the least performing classifier was naive Bayes. Lastly, figure 7 table shows the mean, standard deviation, and accuracy scores of the 2 classifier models on the test set. The model that proved the most accurate was decision tree at 0.89, followed by random forest and then naive Bayes, which corresponds to the confusion matrices in order of best performing to worst performing. Discussion. Statistical In discussing these results, I believe that using statistical models and algorithms are a valid way to classify a data set of this type and differentiate between normal and malicious network traffic. However, these particular models suffer from a relatively weak accuracy score, with the best performing model performing at 0.89. Ideally, I'd like to see a model perform in the 90 percentile. However, most disappointing is that the true positivity rate for all three models are below 60%, with the worst performing model at a mere 30% true positive rate. Limitations. The limitations of this project is that the dataset may have had inaccuracies due to this being captured from a computer network simulation vice a real physical network, and there may have been errors during the cleanup process of converting the raw packet capture into a dataset. Also, the statistical models I use may have had inaccuracies in them due to specific Python libraries used to generate the algorithms, which could account for some rate and score inaccuracies. Future work. The future work that can be performed in this project is to compute the accuracy score and confusing matrices by the 8 different malware classes for more finer detail. In addition, the scores could be computed against the entire dataset vice just a test set for a more higher level overall view. Other things that can be done include plotting out the models to visually show the predicted values against the actual values on a line graph, running more statistical models on a dataset to find out if these models return more accurate results, and lastly, utilizing similar datasets to further train the models. This concludes my presentation. Mahalo.